I should have offered this video long ago, I'm sorry. So this will be about assignment 8, questions 8 through 11, and I'll also talk about springs because since we're not in class, I realize that you don't have much information about springs. So springs are a way of storing energy. We've all seen springs, and some of them stretch and some of them will compress and some of them will do both. So here's a spring hung from a bracket or a bar, and I put a little pan on it so I can add weights to it, and as I add weights to it, it'll stretch. And then for this one, I'll just add weights to it. So these are two different springs, and let's use masses of 100 grams, which if you multiply by 9.8, you'd get 0.98 newtons. So let's just, for now we'll use 10. We'll call them 1 Newton masses. So if I put one of those, if I put one of those masses on here, and I mark where we started, x equals 0, this is the unstretched, and then this will stretch the spring, say, down to here. And let's say this is x equals 8 centimeters. So we have a meter stick here with marks on it. And then if I add, so that brings it down here, and then if I add another one, guess what happens? It'll stretch another 8 centimeters, and the thing will stretch down to x equals 16, and so on. It's linear. The stiffness of the spring, or the response of the spring, is constant, and that's why we call it the spring constant. So the equation that describes this is called Hooke's law. Whoops, what happened? Let me pause. So this is Hooke's law. It says that the spring force will be equal to minus k, that's the spring constant that we're going to talk about, times x. And x is always the amount of distance that the spring is stretched or compressed. Sometimes it's written as minus k delta x, and the reason it's minus is because if the displacement is this way, the spring is pulling up. So the force is opposite the displacement. And just like if I push this down, the displacement will be down, but the spring will be pushing up. And so F is the force of the spring, x is the amount it's stretched, or delta x, the amount it's stretched or compressed, and k is the spring constant. So if we solve for the spring constant, we get that k equals the spring force over x. And since these are in opposite directions, the negative sign goes away. So if we bring this and apply it to the example I just did, we would get, since these masses are 100 grams, which are equal to 90, not 0.98 newtons, but we're just going to call it 1 Newton. So a force of 1 Newton stretches this spring 8 centimeters. And so if we put in 8 centimeters, we will get the spring constant in units of newtons per centimeter, and 1/8 is 0.125 newtons per centimeter. And those units are okay, but more commonly we would do it in newtons per meter. So in that case it would be 1 Newton, the spring force, divided by 0.08 meters, and that would give us 2 decimal places, a spring constant of 12.5 newtons per meter. And so literally that's telling you it would take 12.5 newtons of force to stretch this spring 1 meter. Of course, it probably wouldn't be long enough to stretch that much, but that's the response. And notice if we went to the second set of data, if we took the 2 newtons, right, so let's do that over here. K equals the spring force, in this case 2 newtons, but in this case we're going to divide it either by 16 centimeters or 0.16 meters. And if we take the 2 and divide it by 0.16, we'll get the same thing, 12.5 newtons per meter. So it's constant. The amount of force it takes to stretch the spring another 8 centimeters will always be 1 newton. Of course, eventually the spring gets overstretched, but within the limit of that, the stretchiness or compressiness or stiffness of the spring will be constant. So we don't need to do this too much longer. I think you get the point, but let's compress the spring, and this is, say, a different spring. So I put 1 newton on there, and this is the unstretched distance, and then it compresses it. This is a stiffer spring, so it only compresses at 2.5 centimeters. And you can guess if I add another one, it's going to compress the same distance again, and it's going to go down to 5.0 meters. And so if I use the equation K equals the spring force over the amount I compressed it, I can do either 1 newton over 0.025 meters, or it's going to be equal to the same thing if I do 2 newtons over 0.05 meters, and what I'll get is 40 newtons per meter. So that's the spring constant. So it's stiffer. You see, it's a bigger number. And so in the cart, in the next problem, the cart, this is how we did it in lab. If we were in lab, there's a spring inside the cart, and there's a plunger that goes up, and we just set the cart on the table, and we would add weights. This is what we would do in lab. And we would see how much the weights compressed, and we would get the spring constant of the spring inside the cart of the next problem, problem 8. Okay, let's go there. Okay, I was just about to start problem 8, and I realized I forgot something very important. We didn't talk about potential energy spring or the energy stored in a spring. So on your equation sheet, you'll find that either PE spring, if we write it this way, or U spring is 1/2 kx squared. So just think how that makes sense. The energy stored in a spring will depend on the stiffness of the spring and will depend on how much you stretch or compress it. Why is it 1/2 kx squared? We can actually do that by thinking about energy. And if you're going to compress a spring, you exert a force on it, and you compress at a certain distance. So when you start to press the spring, the force starts at 0, and when you stop compressing it, it's going to be kx. So when you're compressing a spring over some distance x, the average force that you'll use to compress it will be 1/2 kx. And of course, the direction you're pushing the spring and the direction you're displacing the spring is the same, so the cosine is 0, which is 1, and we get 1/2 kx squared. So the work we do to compress the spring will be by conservation of energy, right? The energy stored in the spring. This is actually, for those of you in Calc 2 and integration, this is an integration problem that you might do in Calc 2, where you compress the spring in small steps of dx and the force varies. Anyway, that's the equation for spring potential energy, and we're going to use that in the next problem. So question 8 is a variation of a problem that we do in lab where we actually compress the spring, put the cart against a barrier, and then we release the spring. And when the spring releases, it pushes the cart up the track, and we measure how far it goes up. So this is the reverse of the usual lab exercise that we do under normal conditions. Here, we're going to release the cart. It's going to go down. When the plunger touches the barrier, the cart has a lot of kinetic energy, and so that kinetic energy is going to compress the spring and turn into spring potential energy. And so in this problem, we're given 3 distances, and or 3 positions, and I'll label those, and we'll go from there. Okay, here's the information similar to what's given in the problem. The angle of the track is given, the mass of the cart is given, the beginning position of the cart, the position of the cart when the plunger first touches the barrier, and the final position that the cart gets to before it stops. And the first question is find D, so D is just the difference, this interval. So take the 108 and subtract the 12.4, and you get the first answer, D. So there's D, and the next item is delta Y. We need to know the change in gravitational potential energy, so we need the delta Y of the height. So if I draw a triangle, say from the center of the cart to the center of the other cart, and then a horizontal line up to, so the difference in height, we'll call that delta Y, from center to center, or in the diagram is from the front wheel to the front wheel. That's the change in height of the car. And this angle will be the same theta. So use trig to get delta Y. So the next part, the sine of theta is the opposite over the hypotenuse. The opposite's the delta Y, the hypotenuse is the D. And so delta Y is d sine theta, 95.6 times the sine of 13.2 gives you 21.8 centimeters. Of course, you should only have 3 significant figures in the answer. But when you go to calculate the next question, the gravitational potential energy, you should use that unrounded number. So the PEG is mg delta y, and make sure you get the units right. Why don't you try that? Pause the video and try it. 0.5 kilograms, 9.80 meters per second squared, and 0.2183, 0.2183 meters. It's all the right units. Wow, really writing poorly here. And so the answer is, sorry for the mess, but PEG is mgh, or delta y. So 0.5 kilograms, that's the 500 grams. 9.80 meters per second squared, and 0.2183 meters, and I get 1.06967 joules. That rounds for the answer to be 1.07 joules. Okay, I made some space for the last 2 questions. What is the potential energy stored in the spring when the cart stops? What is PE spring at the bottom? And what's the spring constant? Those are the last two questions. See if you can do those. Think about it before you see what I do. If you just watch me, you don't learn as well. Try and do it. Get the spring potential energy stored in the cart at this position when the spring is fully compressed, and find the spring constant. Okay, the usual approach people take to answering this is to, spring potential energy, let's use this equation so we can get X. It's how much it compressed from 22.9 to 12.4 centimeters. So if we subtract 12.4 from 22.9, we get that the compression of the spring is 10.5 centimeters or 0.105 meters, but we don't have K. So you might get stuck, but no, you should think about energy. If you're thinking energy, look at this situation. We have potential energy, no kinetic energy. We have a frictionless cart, so no work, right? No one's pushing the cart, there's no friction. So the potential energy changes to kinetic, losing potential, gaining kinetic, losing, and then it hits the barrier, and then the potential and the kinetic and a little bit more potential all get stored in the spring. So what's stored in the spring is the energy that we had at the top, because none is lost, there's no friction. And even though there is kinetic energy in the problem, the kinetic energy in the beginning and the kinetic energy at the end is zero. So the delta KE, it goes from 0 to 0. There's no change. This is 0. So mathematically, what's easy to see visually in the energy is a little bit trickier mathematically. It turns out that the work is 0. The change in kinetic is 0. But this delta U, or delta PE, there's two of them. There's U spring, and there's U gravity. And so U spring, or PE spring, either way, U spring equals negative U gravity, and we know what U gravity is. Oops, that reminds me, we made a mistake. I made a mistake when we put in this change in gravitational potential. It was a loss. That should be a negative number. So make sure, I always make that mistake. This is a loss of energy, so it's a negative number. So if we take negative of a negative number, we get a positive number. And so the answer, if you know what you're doing, is very simple. It involves no calculation. The increase in spring potential energy is exactly equal to the loss of gravitational potential energy. So it's the very same number. And since we know the energy and we know the X, we can now use this equation to get the spring constant. So now see if we can get the spring constant. And now to get the spring constant, we use this equation. We just do the algebra. K is going to be 2 times the spring potential energy divided by x squared. And so 2 times, don't use the rounded number, divided by 10.5 or 0.105 meters, must be in meters squared. And that, if I did the calculation right, comes up to be 194 newtons per meter. And the units, I won't go through the units, but they do come out of this. One of the meters cancel on the joules to make it newtons, and that leaves that other meter there. Okay, let's move on to the next one. So the next 3 problems are all the same problem, and actually it's probably a little more challenging for you at this point, but the best thing would be if you do 11 first, then 9 and 10 become trivial. So here's a diagram. Remember the procedure, diagram, free body diagram. This is a combination of force and energy, and a lot of what we're doing goes back to Newton's second law and all that. So here's the diagram. The procedure is now you draw a free body diagram. You're going to use some of the forces. This is our approach to this problem, is mostly a force free body diagram problem. So do the free body diagram before you look at my free body diagram and see how well you can do the free body diagram of this problem. It is similar to a MOPS problem we've done. Okay, don't be lazy. I hope you did it. You'll learn a lot better if you take the lead and do the diagrams. Don't just watch me do it. So anyway, the free object, free body, right? And all the forces acting. So we have an applied force that I'm calling F at some angle. And so I'm going to show the components, the Fx, which is F cosine theta, and the Fy, I couldn't fit it, but it's F sine theta. And since they're not other forces, notice I draw them as dotted lines. There are four forces. These are components of the applied force. The normal force is straight up. The force of gravity is straight down. It's equal to mg. And there's a friction force in the opposite direction, which is mu k Fn. And notice that Fn, although I haven't drawn it that well, Fn and mg are not the only force, because Fn plus Fy has to equal mg. Mg should be a little longer. Okay, so the next step is to write some of the forces, separate it into some of the forces x and y, and write those two equations, and then come back. Okay, see if you get this. So we always start with this. Just notice the formatting. Want you to learn this formatting. So you start with Newton's second law. It's a vector equation. But when we deal with vectors, we always separate the components, because that's the way vector mathematics is done. You can't add things in different directions. So some of the forces in x, some of the forces y, may. And in this case, since the thing is pulled at a constant velocity, the sum of the forces in both directions are 0. So we add up the forces. We see F cosine theta as the positive x force, and the friction force, or mu k Fn, as the negative force. So I put the negative sign in. That means I'm just going to use the magnitude of this equals 0. And two positive forces, Fn and Fy, which is F sine theta, and one negative force, mg. Now look at these equations and think about what is unknown and what is known, and then think about how we're going to solve it. So there were two unknowns, the applied force and the normal force. And the question that you're asked in number 9 is to find the normal force. So the logical thing to do is we have two equations and two unknowns, is to eliminate F. So that's an algebra issue. So you want to eliminate F and get one equation for Fn. See if you can do that. Try your best. Hopefully you can do it, and then come back and I'll show you what I do. Okay, algebra. We use a lot more algebra than anything. Maybe trig second. Calculus only concepts, really. So we want to eliminate F. So what I did was I solved for F. Hope you can follow that. And then once I have F, I just substitute it in here. And I get Fn equals F mu k Fn over cosine theta times the sine of theta. And then I brought this over the other side of the equation by adding it to both sides. And then I factored out the Fn. You got to be careful about that kind of factoring. So factor out leaves a 1 here, and leaves mu k tan theta, sine cosine is tan, here. And then when I solve it, I get that Fn equals mg 1 plus mu k tan theta. But if you look at the question 11, you'll see this there, but these are reversed, right? So that's okay. You can have 1 plus this or this plus 1. It's the same thing. So you can find that in question 11 and check that off. So I'll leave it up to you to put the numbers in there and do the calculation. And then the next question is, what is the force of friction? So how are you going to get the force of friction, the tension in the rope, and the work done by pulling the crate? So think about those three questions and try to do them now that we've done this much. See if you can do that on your own. And then when you're done, come back. Okay, the rest of it is pretty straightforward. Once you have the friction force, once you have the normal force, the friction force is just mu k Fn. And so multiply that out, that's easy enough. And then they're calling it the tension force in this problem. It's T. I should change it to, I should probably change it to Ft. Anyway, the applied force, the tension force, we know that the tension force, the applied force times the cosine of theta is equal to the friction force. And so if we divide by the cosine of theta, we get the friction force divided by the cosine of theta gives us the applied force or the tension force. And that force times the cosine of the angle, which just gives us back the x component. Remember, Fr cosine theta, so the F, that tension force times the cosine of the angle, gives us that x component, times the distance, will give you the work in the right units. So that should allow you to do that. So number 10 is a similar problem but with different numbers, but you have all the equations, and so you can just use those to do number 10. But in number 11, you're actually required to derive the generalized equations for all those different quantities. So let's begin to work on number 11. We have Fn here, which we've identified, and we know that F fric is mu k Fn, so derive the generalized expression for F fric, and once you've done that, come back and check. So F fric is pretty easy. We have Fn, so we just substitute Fn in, and we have the mu this way, and as you'll notice in the assignment, these are reversed, but that doesn't matter. And now we want the applied, what I was calling the applied force is the tension force, or Ft. So we have that right here, right? We had that, we started with the equation before that F cosine theta is equal to the friction force, and so I divided by the cosine theta, and so this equation is in fact the Ft, what I was calling the applied force, or the tension force of the string, is just this. So once again, substitute in for Fn and find the generalized expression for Ft. More algebra, you should be getting good at it. So Ft is mu k Fn over cosine theta. So we have the mu, I dropped the little k, the mu, and then we have this, so that goes in here, but in the denominator we have to multiply this by the cosine theta, right? Because this is our Fn, and the mg is the top, and this is in the bottom, times the cosine. So when I multiply the cosine by 1, I get cosine. When I multiply the cosine by this, remember that tangent is sine over cosine, so the cosine cancels. And so you end up with this expression here for the Ft. You should be able to find that in the list. And the last thing is to find the work. So now we have the ft times the cosine times r, which is given in the problem as being d. So do that one. So getting messy, we have the work is ft, so here's our ft, that has to go in here, times the cosine of theta times the distance, which in this case is given as d. So we have mu mg cosine theta d, and then in the denominator we have this, and you'll find this in the list, but be careful, this is pretty messy and it can be simplified. So there is one other choice in the list of selections where you have to simplify this using trig. I'm going to let you figure that one out on your own.